Hello, everyone. Welcome to my poster, and thanks for joining in. I'd like to share a quick overview of some work we've done recently on pooling conformational ensembles and the effect this approach has on predicting binding affinity of small molecules to their protein targets. Deep learning methods for structure-based affinity prediction have attracted a great deal of interest in the last few years, and at Atomwise, we've used our method called AtomNet for a variety of virtual screening and affinity prediction tasks with good success. However, most such methods are trained and tested on static structures of the protein-ligand complex. And of course, we know that under experimental conditions, proteins and small molecules are dynamic and sample multiple conformations. A binding affinity measurement is a measurement of the experimental ensemble, suggesting that the best predictive methods will also take into account these conformational dynamics. Ideally, we'd make predictions by training our network on robustly sampled Boltzmann-weighted ensembles using a high-quality force field. But as a first step in proof of principle, we sought to explore the quality of predictions on smaller ensembles. We considered two types of ensembles, one generated with local sampling of the ligand around a crystal structure, and one generated by sampling the protein as well. We experimented with multiple pooling methods and found that the best results when examples are pooled during the voxelization step, creating an atomic density-like representation from multiple sampled conformations. We aim to use these methods to lay the groundwork for predictions based on more robust conformational sampling, such as through molecular dynamic simulations of protein-ligand complexes. To give a very brief walkthrough here, you'll see our methods described in the middle column of the poster, where we first illustrate the types of conformational ensembles we used for our experiments, including local sampling around a crystal structure and larger scale sampling of the protein. At the bottom of that column, we illustrate the two families of pooling approaches we examined using our 3D CNN-based architecture, pooling at either the input or the output of the network. Pooled voxelizations are illustrated on the right side, showing that this method produces an atomic density-like representation of the ensemble. In the third column, we show three examples of applications, one on the locally sampled crystal structures at the top, where we find that sampled ensembles up to an amplitude of about 3.0 angstroms improves affinity prediction. And on the bottom, you'll see protein sampling showing both the input and the output pooling strategies and illustrating faster training in the pooled case compared to baseline. We're excited about further exploration of these methods because they can enable the use of very large numbers of conformations, thousands of examples to be used in affinity predictions. So thank you for stopping by our poster, and please do get in touch if you have any questions.